In today's video, we are going to solve problem number 12, highly divisible triangular numbers. I'm going to start by copying this in here like we normally do and saving this. Okay, so here's what the problem states. The sequence of triangle numbers is generated by adding the natural numbers. So the seventh triangle number would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 equals 28. Then you list the factors of each of the first 7 triangle numbers, 1, 3, 6, 10, 15, 21, 28, less their factors. And then you can see that 28 has 5 divisors. So what we need to do is find the value of the first triangle number to have over 500 divisors. So this problem has 2 steps. First, we need to generate triangle numbers, and then we need to find factors for this number. In order to do that, since we don't know how many triangle numbers we're going to have to generate in order to find one with over 500 divisors, we are going to use a while loop. And we're going to use this number as our main triangle number generator. So I'm going to create a for loop in here, and I'm going to plug in this into here. And then I'm going to use an add array elements from these numbers. And I'm going to run this for, let's see, less than, let's just say 10 for now. Create constant, whoops. Replace comparison for less or equal. I'm going to take this number and make it create constant less than or equal to 10. I'm also going to increment these so I don't add the zeros into here, actually. I don't want zeros to be part of this array, not necessarily because I know that there will be a problem, but I suspect there might be. And then we're going to take this guy, tunnel mode, indexing arrays, and create an indicator here. So what this should give us are the first 10 triangle numbers, and let's see if they match. Oh, it's got to be greater than or equal to. This, oops. Come on, there we go. We're going to replace this with a greater than or equal to. There we go, that should work. So we should get the first 10 triangle numbers. 1, 3, 6, 10, 15, 21, 28. This looks correct, especially based on the list that we've got here. So the next thing we want to do is check to see how many divisors this number has. So I think the way that I'm going to do that is I'm going to take this number, and I'm going to use the last value, and I'm going to plug this number into here, and I'm going to increment this, and then I'm going to use that quotient remainder, and I'm going to take that number and divide it by this number, and then I'm going to take the remainder, and as long as this remainder is equal to 0, I'm going to index that number. And so to do that, I'm going to put this conditional statement here. And this is going to be called create indicator divisors. And this is going to be triangle numbers. And I'm actually going to rewrite this to do the first 7 because I want this last list of divisors here to be the same as the 7 case here, so I can check it. So I'm going to run this again. 1, 2, 4. What's happening here? I was expecting this to be 28 like it is here, but it's only giving me 1, 2, and 4. I should also have 7 and 14 and 28. So what is happening here? Let's probe this wire. I suspect maybe it's something here. 7. Okay, so this should run 7 times. Oh, okay, that makes sense. We're only going up to 7, not to 28. So I need to take this number. That's where my mistake is. I need to check at least all the way up to the current triangle number being judged. So let's see here. There we go. Oh, and I suppose I need to also include the number itself. So this is kind of inefficient. But I don't see another way to do this off the top of my head. That's okay. We're gonna because we're decrementing every time we check it, but that should be okay. Oops, that is not right. Oh, this one here. I know what I did wrong. I need to increment this here to include the very last number. That's my mistake. I don't want to decrement the number going in to be divided by. I want to increment the number of numbers that it looks up. Okay, there we go. 1, 2, 4, 7, 14, and 28. Okay, so now all I have to do is check the array size here. And as long as this number is greater than 500, and it does say what is the value of the first triangle that have over 500. So if it had 500, that doesn't count. When this happens, oh, I already had this. I need to plug this number into here. I had some logic like that almost already set. Then I believe this should give me a final triangle number that has over 500 divisors. Let's see here. Let's run this and see what we get. Okay, I am going to stop this. Visible items, vertical scroll bar, and yeah, so we're only like 15 divisors in. Okay, so one thing I'm going to do is I'm going to delete this. And I'm going to take just the last value of this divisors. And the reason I'm doing that is because I'm going to look at this, create an indicator. Current number. Because if I minimize the number of indicators I have here, that will speed up my algorithm. So we're going to do this, and we're going to check this, and I'm actually going to do this number of divisors. Oops. Divisors. And then we will run this again. Okay, after watching this, I can see that this number is getting fairly high, and it is very slow the higher this number gets because I'm having to generate multiple for loops. So what I'm going to do is I'm going to stop this, and I'm going to find a more efficient way to do this. I'm not sure how I'm going to do this, so I'm going to think about it for a little bit, and then I will update you once I'm done. Okay, so I did make one change. You can see it's much faster now. I'll explain what I did. Rather than generating a new for loop, rather than generating a new array of triangle numbers every time, so adding 1 plus 2 plus 3 plus 4 every time, I put 0 in a shift register, and I added 1 and then 2 and then 3 and then 4 to it every time. And rather than recreating that array every time and then adding all those elements, I do them sequentially. So I never keep an array of all the numbers required to make a triangle number. I just add them incrementally, one iteration loop at a time, and that eliminated an entire for loop from my algorithm. I think I can make this part more efficient here. I'm trying to think of how to do it, so I'm going to stop this. You can already see it's going a lot faster. I don't know where this is going to stop, but I'm already at 9 million something. So I'm going to see if I can make this part more efficient here. Okay, so I am realizing now that, like, in order for me to check all of these divisors, I'm going to have to check every number against every triangle number. So maybe there's a way to do this more efficiently, but I'm not exactly sure what it is. So rather than try to do that, I'm going to time this VI and oops. Because I'm just kind of curious how long it's going to end up taking to execute. So we've done this before. I'm going to add a frame before and after of this time sequence structure. Oops. Add frame after. Sorry, this flat sequence structure. And I'm going to take the high resolution relative seconds, And I'm going to subtract the final minus the initial and create an indicator. Oops. Create an indicator. Execution time. Whoa. Execution time. And this is going to tell me how long it actually took this algorithm to execute. I'm also going to, I'm checking the current number already. I think, want this inside because I want to be able to see how many we're actually getting and if kind of what that looks like. It'll be moving really fast, but as we get up higher, I think I'll start to see larger and larger numbers and know when we're getting close to find one that has 500 divisors or more. So I am going to run this again, let this run. I think I can tolerate this runtime. I'm now over 1 million. It's going to take longer and longer time to calculate because I have to cycle through more and more numbers with this for loop. But I think if I had to guess, this would be like somewhere in the like several hundred million or something. So like this is an amount of time that I could tolerate actually waiting. Whereas before it was definitely way too slow. It probably would have taken days for it to actually compute, but this might take a few minutes. So we're going to let this run, see where it stops, and we will check the answer once we're done. Okay, and it is done with a number of 576 divisors. The number is, let's see, 76,576,500. So let's pull up our, and we'll go to problem number 12. And there we go, 76,576,500. So there you have it, problem number 12, Project Euler. Have a good one.